Let's start our lecture on section 8.9 by looking at 3 examples of differential equations. The first example that I'm showing you has a second derivative of the function y as well as y itself. Okay, so the original function y and its second derivative exist in the same equation, and that's what makes it a differential equation. The order of this differential equation is 2 because the highest derivative I have in the problem is a second derivative. Okay, it has nothing to do with the exponents in terms of it being linear, quadratic, anything like that. Order is completely different. Here's a second example where you can see that I have dy dx, and that of course represents a first derivative. So I've got a first derivative of a function y with respect to x, and then the original function y itself, all within one problem. Here the order is first order because I've got a first derivative only. My third example just utilizes a different notation. As opposed to dy dx, I have y prime of t, which still just means first derivative. So although this equation is a quadratic differential equation, whereas the other ones are linear differential equations, we still have a first order differential equation in that third example because of the first derivative. So the kinds of differential equations that we are going to look at in solving in Calc 2 are separable differential equations. Separable differential equations. So in the PowerPoint we defined what that meant, and now I'm going to go through the overall process that you would use when solving a separable differential equation. Remember, the goal of solving a differential equation is to find a function y that would satisfy the equation. So the first thing is just a note. And you can see here that differential equations might use prime notation, or they might use this dy dx notation. They are interchangeable, but often the dy dx notation is going to be better. It's going to be more obvious in terms of how we utilize the dy and dx, how we utilize that derivative. So I would always change my primes into that notation. Alright, once we've done that, the first idea is to actually separate the differential equation. Since it is separable, then we need to separate it. And that means to use our algebraic manipulation so that we're bringing all of our y terms over to one side of the equation and then all of our x terms over to the other side of the equation. Now I say x, but really that could be any variable. We could be working in terms of t or any other letter variable. But the idea is all like lettered variables should be on one side and then the others should be on the other side. Now this includes your dy or dx. So that's why this notation is better, because what I'm going to want to do is separate these so that they're on opposite sides of the equation. The dy will go with the y's and the dx will go with the x's. Once I've separated so that I have y terms equal x terms, then I'm going to integrate each side of that equation. And you can see why we want dy over here with the y terms and why we want dx over here with the x terms, because that is necessary in order to do our integration. When you integrate these indefinite integrals on both sides of the equation, they'll both result in adding constants of c. However, if you have two constants, each one on a different side of the equation, you could combine those two constants into a different constant, still called c, but you'd only need to note it on one side of the equation. So that's often what you'll see, is you'll see plus c added to only one side. That just means that the two constants were combined. From here, our final step is going to be to figure out what y is equal to. So remember, the original goal is to find a function y that satisfies the differential equation. And so what we're going to have is a bunch of terms. One of them should have a y in it, and we're going to isolate that y variable using our algebra. If the particular solution is something that is asked for, in other words, if it gives you an initial condition of some sort and you need to solve for c, then you should do that as well. But otherwise, that's all there is to it. So let's look at using this process to solve a first order linear differential equation. And then you might have seen in the PowerPoint there's actually a formula that you can use that makes that work much faster, and I would definitely encourage you to use it. But the process of how to come up with that formula and how we're solving might be helpful when you're solving some other problems. So I'm going to show it to you anyway, and then we can still use the shortcut to compare how we get the same answer either way. So here's the example that we're going to work on. So what I'm going to do is I'm going to give you a differential equation, and it's worth noting that this is a first order linear differential equation. Let's go through some of this process here that I outlined above. First things first, I want to get rid of y prime, and because it's a function of t, I'm going to use dy over dt to replace that notation. And then I'm going to need to separate the differential equation so that all my y terms are on one side and all of my t terms are on the other side. So my first move might be to multiply both sides of my equation by dt. But then I need to take this expression, not necessarily the -4, but since they kind of come as a package, we might as well. But I need to take this expression and I need to get it over here on the other side. So since it's being multiplied by dt, the move would be to divide by it. So what you're seeing now is your separated differential equation. We're not done. We've only really accomplished step 1, but I just wanted to note that you're separated. All of your y terms are on one side, all of your t terms are on the other side. Okay, so what we need to do at this point is to integrate both sides. And so we're going to be taking the antiderivative, essentially, of 1 over 3y minus 4. And then here, we're taking the antiderivative of really just 1 dt. I'd like you to try to integrate both sides, hopefully utilizing all of the strategies and techniques of integration that we've worked on in the past 8 sections of this chapter. And I'd like you to try to integrate, and then you can pause, work on that, come back, and we'll check to make sure that that was successful, and we'll continue solving for y to finish off the solution. Here are the antiderivatives of each side of that differential equation. On the left side, you could possibly use a u substitution to let u equal 3y minus 4, and then you'd be integrating 1 over u adjusted by a constant of 1/3 because of that 3 there. Or if you look at the table of integrals from section 7.6, I want to say, hopefully I'm remembering that right, or 8.6 in this book. Anyway, if you use the table of integrals, there is a formula that you can look at as well. On the right side, the antiderivative of 1 with respect to t is going to be t, and then here you're seeing that I have a constant added just on one side. You can add it on one side or the other. If you add it on both, they can be combined. So there's my antiderivative. Let me solve this equation for y to finish this problem off. I'm going to to get rid of this 1/3. I'm going to multiply through the entire equation by 3. That'll give me the natural log of the absolute value of 3y minus 4 is equal to 3t. And if I multiply c by 3, it's still just a constant c. Remember, we're never trying to quantify a constant c, we just want to note that it's a constant. From here, you need to get this y variable, or in fact this entire term, the argument of the log, out of there. And the only way to do that is to undo the log by taking e and raising it to this power. So remember that is how you convert from a logarithmic equation into an exponential one. And what that will do is it will isolate the argument. So if I raise this side of the equation e to the natural log of 3y minus 4, the property of log says that e and natural log are going to cancel out. So on the left side of the equation I have 3y minus 4, and on the right side of the equation I have e to the 3t plus c. Now this is a little bit interesting what happens next, because right here you can separate this constant c and show that it actually becomes a multiple, a constant multiple. If you think about separating this into e to the 3t times e to the power of c, I'm sort of working backwards here, because one of the properties of exponents is if two exponents have the same base, you can combine them together by adding their exponents. So that's essentially what we already had. But if I go backwards and I undo that, then I end up with e to the 3t times e to the power of c. E is a constant, and c is also a constant. So although that looks weird, what I have is constant raised to the power of constant, which in the end is just a constant. So that whole side of the equation can be written as some constant c multiplied by e to the 3t power. And that's the trick here that you might need to use in some of the other problems where there isn't a nice formula and you don't have a shortcut. You actually have to go through the work of separating the differential equation and then solving. You may run across this where you have to first of all change it into exponential form to get the argument out of the natural log, and then also recognize the fact that e to the c is just a constant multiple of c. Finishing this off, I need to solve for y, so I need to add 4 and then divide everything by 3. And so what I'll get is c times e to the 3t plus 4, again all over 3. We're going to, once again, group constants together. If I take that 3 and I divide it into each term of the numerator, I have a constant divided by 3, still just a constant. It's a different constant, but we don't care, as long as it's still just a constant. And so this is the final answer. This is the solution to that differential equation. We're saying that the original function was y equals c, some constant, times e to the 3t plus 4/3.